This unit, we're going to talk about momentum, and momentum is derived from Newton's second law, as I've mentioned in previous lectures. So let's go over Newton's second law for a second. Newton's second law says every action has an equal opposite reaction, which also means every force has an equal and opposite force. And because forces produce accelerations, for our purposes of discussion here, we're going to say that every acceleration has an equal and opposite acceleration. Now, what does this mean in a real-world context? We don't always see that. For instance, if someone jumps up off the surface of the Earth, clearly they've managed to accelerate themselves upwards, right? They're flying upwards and they didn't used to be. But it's not obvious that the ground is accelerating downwards. Now, the thing is, the ground is accelerating downwards. It's just accelerating downwards in a really small amount, so you can't see it. Now, velocity is just acceleration times time, which means that if something like a rocket or a helicopter manages to pull itself up in the air and it accelerates upward to give itself a new upward velocity, then something else needs to accelerate downward for a similar amount of time. And in this case, let's say it's the Earth that's accelerating downward. But now acceleration depends on mass. So the Earth has a mass that is very large. The rocket has a mass that's very small. And what that means is the acceleration of the Earth is going to be very small, whereas the acceleration of the rocket is going to be relatively large. So that means that even if the rocket has a large change in velocity, because velocity is just acceleration times time, the Earth is not going to have a large velocity. So as a result, we can't just look at the velocities, because the velocities aren't going to be the same. What we can look at is velocity times mass. Because the forces are really the same, and force equals acceleration times mass. And then the accelerations were dependent on mass, and then the velocity is dependent on acceleration. So as a result, the mass affects the velocity. So now the mass times velocity in both cases is going to be a constant, and we call this constant momentum. And momentum, which is often written as a P, you say momentum equals mass times velocity. And it's at a closed system, when you're looking at all objects inside a system, momentum is always constant. And momentum is a vector because velocity is a vector, and that's the symbol for vector. And what that means is which direction your momentum does matter. So let's start with a very simple two-dimensional case. A truck's driving down the highway. It's a big truck. And we'll just say it has a mass of 2 for now. 2 what doesn't really matter in this case. And it collides with a car that has a mass of 1. So now we need to decide what speeds they're going at. We'll say the truck is going at 10 meters per second, and the car is going at 5 meters per second. And we're just going to say they collide and they get all mangled together and stick together, and we have to figure out what is their final velocity. So let's take this a step at a time. Let's find the momentum before they collide. 10 meters per second times 2 mass. And I know it's confusing. That one means mass, not meters. I should have picked better units. That's going to equal 20 meters per second times mass. And in this case, it's 5 meters per second times 1 mass. So 5 meters per second times masses. And they're both going in the same direction here. And what that means is we can add them together. So the total momentum is 25 meters per second times mass. So that's what's going on before the collision. We have a momentum of 25. So now after the collision, what's going on? Well, they're stuck together, so we can treat them as having 1 mass, and the mass doesn't change, right? Everything's still there, nothing important's flown off. So as a result, we can say that mass equals 3. So our momentum is 25 equals mass times velocity, and mass equals 3, so that's 3 times velocity. So now we can just solve it just like an equation. We divide both sides by 3, and velocity equals 25 thirds. And if you remember, our units for velocity were meters per second, so that's in meters per second, and that comes out to 8.3 repeating meters per second. So they're going to stick together, and they're going to end up going slower than the fast one was going, but faster than the slow one was going, somewhere in between. And the thing is, it's not an exact average. An exact average would be 7.5, and it's not that. And the reason for that is the truck has more mass. And because it has more mass, its momentum is more significant. So our result should be closer to the speed of the truck than to the speed of the car. And when we look back, it is. 8.3 is closer to 10 meters per second than it is to 5 meters per second. So this is a fairly simple example. We'll talk about more complicated examples a little later on, about things we can do with multiple dimensions and other things. But for now, I hope you understand this.